Hello friends, welcome back to my YouTube channel. Today I'll be talking about how to select the extracting solvent for liquid extraction. So this would be seventh part of my discussion on liquid extraction, and the title that I have given to this discussion is Choice of Solvent. How to select the extracting solvent. So at the end of this discussion, you'll get an answer to this question. How to select the solvent for liquid extraction. How to select the extracting solvent for liquid extraction. So this is very important topic where you will be asked questions on this. How you'll be selecting the solvent in liquid extraction. So at the end of this discussion, you'll come to know what points or what is the criteria for selecting a liquid and extracting solvent for the operation of liquid extraction. So let us start the discussion. There is a variety of liquids that are available which can be used as extracting solvents, and you need to choose one of these liquids. Many of them can be used, but you cannot select the extracting solvent randomly. You have to consider some points. You have to consider some parameters before you select the extracting solvent from the variety of liquids that is available. So many liquids, as I said, they can be used as extracting solvents. Many liquids are available that can be used as an extracting solvent. For example, water. You can use water as an extracting solvent in many extraction operations. And as you know, water is the universal solvent. Water is said to be the universal solvent. Then there are many organic solvents, organic liquids that can be used as extracting solvent. For example, you have benzene, you have toluene, you have methyl isobutylene ketone, diethyl ether, methanol, ethanol, hexane, chloroform, and many other organic liquids. You need to choose the appropriate one, the appropriate extracting solvent from the variety of liquids that is available. And that is important task, because you cannot select the extracting solvent randomly. You need to consider some criteria for selecting the extracting solvent. Even though you have many liquids, there is not a single liquid that has all the desirable properties. All desirable properties that are required for an extracting solvent, they are not present in any one liquid. So no single liquid has all the desirable properties. You need some compromise. Some compromise is always required. It is always necessary to select an appropriate extracting solvent, or to select an appropriate liquid as an extracting solvent. So you need to make some compromise in order to select, because you are not going to get all the desirable properties in one liquid. So that's why a compromise is always necessary to select an appropriate liquid as the extracting solvent. We need to consider various criteria for selecting the extracting solvent. Various criteria need to be considered while selecting an extracting solvent for the given extraction task. And what is this criteria? We are going to understand in this discussion. Okay, so at the end of this particular point or this particular discussion, now we know that there are various criteria that has that have to be considered while selecting the extracting solvent. Now let us know what are criteria. So criteria for selecting the extracting solvent. So let us understand this thing. The first criteria that you can or you have to consider is selectivity. Let me first tell you, selectivity is a parameter, and while selecting the extracting solvent, you need to consider this parameter. So first of all, we are going to understand how selectivity is defined and then how to use it for selecting the extracting solvent. Selectivity. So selectivity, it is a measure of the effectiveness of extracting solvent for separating the components of a liquidation by extraction. So selectivity, it is a parameter, it is a measure of the effectiveness of the extracting solvent for separating the components of a liquid solution by extraction. So selectivity tells you how effective is the extracting solvent, how effective is the extracting solvent in separating the components of the feed solution. During extraction, the solvent, we know what happens in our discussion. We have denoted solvent by B. So during extraction, the solvent B is added to the solution of A and C, which is the feed solution. And then this solvent will be extracting solute from the solution of A and C. A and C, A is the carrier solvent and C is the solute that is to be extracted. So the task is to extract C from its solution with A by using solvent B. So during such extraction, so for example, what are you doing? You are adding solvent B to the solution of A plus C, and then you are mixing it properly. Then you allow this mixture to settle, which will then be separating into two layers. As you know, we are considering a system where C is soluble in A and B, but A and B, they are soluble in each other to a limited extent. This is a common situation or common case that is found in liquid extraction. C is soluble in A and B, and C and B, they are soluble only to a limited extent. I have talked about it in my earlier videos. I'm giving link to the playlist which has all my videos on liquid extraction. You please watch all those videos. Okay, so A and B, they are soluble only to a limited extent. So if you are mixing these two, solution of A and B and V, and then allow the resulting mixture to settle, then there will be formation of two layers. One will be A layer and the other will be B layer. Then solute C will be getting transferred between the two layers. And after sufficiently long time, the rate at which C moves from A to B becomes equal to the rate at which it moves from B to A. So at that point of time, we say that you have a dynamic equilibrium where concentration of C, where there is no net transfer of C across the interface between the two phases. But since A and B, they are soluble to a limited extent, the A layer will also contain little amount of B. So in that case, we call that as A rich layer. In the same way, B layer will be containing little amount of A in it, in which case we call the layer as B rich layer. So A rich layer is the raffinate layer, and B rich layer is the extract layer. And these two layers, they will reach equilibrium. There will be a dynamic equilibrium between these two layers, where even though C is transferring across the interface, but the rate at which it is transferring from A rich phase to B rich phase is same as the rate at which it is transferring from B rich phase to A rich phase. So there is no net transfer of C across the interface. So when this happens, we'll say that raffinate and extract phases, they are in equilibrium with each other. Then we define selectivity when there is equilibrium between raffinate and extract. That's why I discussed how equilibrium is reached. Selectivity is defined when raffinate and extract phases are in equilibrium with each other. And how it is defined? It is defined as the ratio of ratios of concentration of C to the concentration of A in the extract phase and raffinate phase, in the extract and raffinate phases when they are in equilibrium with each other. So we have to compare ratio of C to A in the raffinate phase to the ratio of C to A in the extract phase. So we will be comparing this ratio. So in the raffinate layer, you have ratio of concentration of C to concentration of A, and in the extract phase also you have ratio of concentration of C to concentration of A. So this ratio is nothing but the selectivity. So that's why it is defined as the ratio of ratios, these two ratios, ratio of these two ratios. Which two ratios? Ratios of concentration of C to concentration of A in the extract and raffinate phases when they are in equilibrium with each other. Are you understanding it? So we are talking about ratio of concentrations of C to A in each phase, raffinate and extract phase, when they are in equilibrium with each other. And this ratio of ratios is called selectivity. We are going to write a mathematical equation for that. Then you'll understand it. So we will do that next. We will know how to write an equation for the selectivity. Okay, so selectivity is then defined. We just saw the definition. It is the ratio of ratios of the concentration of C to the concentration of A in the extract and raffinate phases when they are in equilibrium with each other. When the raffinate and extract phases, they are in equilibrium with each other. So mathematically, selectivity, which is denoted by beta, so beta will be concentration of C divided by concentration of A in the extract phase, and this entire ratio divided by concentration of C upon concentration of A in the raffinate phase. So you have two ratios. There is one ratio in the numerator and there is another ratio in the denominator. So this is ratio of these two ratios. Beta, that is the letter that we use or symbol for selectivity. Beta is equal to concentration of C divided by concentration of A in the extract phase. This divided by concentration of C divided by concentration of A in the raffinate phase. So this is how you define selectivity. And usually in liquid extraction, concentration is expressed in terms of weight fractions. In liquid extraction, we are going to express concentration in terms of weight fractions. So if you use that, beta will be weight fraction of C divided by weight fraction of A in the extract phase divided by weight fraction of C divided by weight fraction of A in the raffinate phase. A ratio of weight fractions of C to A in extract phase divided by ratio of weight fraction of C to A in rapid phase. So this is how we define selectivity. We still have to understand how selectivity plays a role in the selection of extracting solvent. We are going to understand that shortly. So this is the mathematical expression for selectivity. Selectivity is also called the separation factor, and for useful extraction, selectivity has to be greater than 1. It has to be greater than 1. That is important. Then and then only you can have full extraction. You will be able to extract solute from the feed solution. So beta has to be greater than 1. That is important thing. So better results are obtained as beta increases beyond 1. As the value of selectivity increases above 1, you get even better results in liquid extraction. For the case where A and B are soluble to limited extent, on the case that we have talked about, beta will be equal to 1 at the plate point. So you must be remembering the plate point. And for a system where A and B are soluble to a limited extent, beta is equal to 1 at the plate point. For some systems, beta decreases from a higher value. There are some systems for which beta will be decreasing from a higher value. It will pass through 1 and then take fractional values. So for example, beta may decrease from 3.5 to 1 to 0.56. So beta is decreasing. In this case, in this example, beta is decreasing from a higher value of 3.5. It is passing through 1 and then it is becoming a fraction. So such systems, they are analogous to azeotropic systems of distillation. So such systems are analogous to azeotropic systems in distillation. Azeotropes means constant boiling mixtures where there is no much difference in the boiling points of the components. Okay. So when beta decreases from a higher value, passes through y or becomes 1 and then finally takes fractional values, then this is analogous to azeotropic systems of distillation. Azeotropic mixtures are those mixtures where, or those liquid solutions where there is no much difference in boiling points of the components in the solution. And in that case, their separation by using distillation is not possible, because distillation is possible, or distillation is based on difference in boiling points of the components that are present in the liquid solution. And if there is no much difference, then there will be no separation by using distillation. And in the case of liquid extraction, this happens when selectivity takes this value. So it is initially very high, then it becomes 1 and then it takes fractional values. I hope the concept is clear to you. It is analogous to relative volatility of distillation. Okay. So beta, the selectivity or the separation factor, it is same as relative volatility in distillation. It is analogous to relative volatility of distillation. An extracting solvent that gives beta greater than 1, that must be selected. So at the end of this particular discussion, we now can conclude that you can select an extracting solvent from a variety that is available, an extracting solvent that gives selectivity greater than 1. And as selectivity increases beyond 1, then you're going to get even better results. So if you have two solvents, let us just, for the sake of understanding, you have two solvents, B1 and B2. And for B1, let us say beta 1 is 2.8, and for the other solvent, that is B2, beta 2 is, let us say, 4.2, for example. Then obviously you are going, this is beta, you are going to select the second shape. What is the basis of selection? How you have used selectivity as a criterion for selecting the solvent? You are selecting a solvent that gives a higher selectivity. Are you understanding it? So that is the thing that you have to remember in this case. So an extracting solvent that gives selectivity well above 1 must be selected. Are you understanding it? This is how you can use selectivity, or you can use the parameter beta, that is selectivity, for selecting the extracting solvent. I hope the concept is clear to you. So if somebody now asks you, how are you going to select the extracting solvent based on its selectivity? You simply say, I will select that solvent which will give selectivity that is much higher than 1. Because then and then only I am going to get better results in extraction. Are you understanding it? So I hope this is clear to you. If you have any doubts, you please mention them in the comment section. Then the next parameter or the next criterion is distribution coefficient. Again, this is a parameter. First we will define it, we will understand what is it, and then we will know how this parameter can be used for selecting the extracting solvent. So distribution coefficient, it is a parameter that gives the distribution of C between the extract and raffinate phases when they are in equilibrium with each other. Now we again are talking about a situation where extraction has taken place and extract and raffinate phases are obtained and they are in equilibrium with each other. So at equilibrium, how solute C is distributed between the two phases, extract and raffinate phases, that is given by a parameter, and we call that parameter as the distribution coefficient. So let us understand. So first let us know the definition. Distribution coefficient is defined as the ratio of concentration of C in the extract phase to the concentration of C in the raffinate phase when they are in equilibrium with each other. We are taking the ratio of concentrations in the two phases when they are in equilibrium with each other. So mathematically, you can write K, the distribution coefficient, it is denoted by K. So K will be concentration of C in the extract phase divided by concentration of C in the raffinate. And if concentrations are expressed in terms of weight fraction, in that case K will be weight fraction of C in the extract phase divided by weight fraction of C in the raffinate phase. That is K is equal to Y star upon X, where Y star and X star, these are in equilibrium with each other. That is, Y star is concentration weight fraction of C in the extract phase, X is weight fraction of C in the raffinate phase. When extract and raffinate phases, they are in equilibrium with each other. You please remember, we have defined selectivity when raffinate and extract phases were in equilibrium with each other, and distribution coefficient is also defined when raffinate and extract phases, they are in equilibrium with each other. Okay? So right now we know the definition of the distribution coefficient. It is not required that K be greater than 1, as was the case with selectivity. Selectivity has to be greater than 1, but K may not be greater than 1. K doesn't need to be greater than 1. but higher values are always desirable. Higher values of K are desirable. That is the thing. Because if you have higher values of K, then you'll need lesser solvent for the extraction. So that will reduce cost. So remember, when you are using solvent that gives higher values for K, then you'll need lesser amount of solvent in the extraction, and that will reduce the cost. So what would be our conclusion for this particular point? A solvent that gives higher K, it needs to be selected. So we are going to select based on distribution coefficient. We will be selecting a solvent that gives higher K, higher values of distribution coefficient. Okay, so I hope this point is clear to you. Now let us move to the next point. Then the other criterion is solvent insolubility. So in this case, in order to understand this, first you should know that formation of two insoluble phases, that is raffinate and extract phases, which is very much essential. It is desirable. These two phases have to be formed for successful extraction. So formation of two insoluble phases, which are the two insoluble phases, raffinate and extract phases, it is desirable for useful extraction. This formation, it depends on extent to which B is insoluble in the solution of A and C, which is the feed solution. So the extent to which B is insoluble in the feed solution, that is solution of A and C, will decide how easily the two phases will be formed. How easily raffinate and extract phases will be formed. So more the insolubility, the easier the formation of two phase. So more insolubility of solvent B in the solution of A and C is desirable in this case. So more the insolubility, the easier the formation of the two insoluble phases, that is raffinate and extract phases. For a given solvent, the formation also depends on concentration of C in the solution, A plus C solutions. So it not only depend on the insolubility of solvent, it also depends on concentration of C in the A plus C solution. So for example, let us look at a system whose ternary equilibria is now shown on this equilateral triangular graph. So this is obtained with solvent B1. You'll be getting the binoodal solubility curve. And let us consider another system that is obtained, another system with other solvent B2. So you have the same solution of A and C, and this time you are using some other solvent. Let us say that it is B2, and you get the binoodal solubility test like this with solvent B2. Now, I'm drawing a tangent that starts tangent to the binoodal solubility curve that originates at the apex B1, and I'm calling this point as D. I'll do the same thing for the other diagram. I'll draw a tangent from apex B2 and I'll be getting point D. Okay. So now let us understand where we are understanding this point. What is the point? How concentration of C is important. How concentration of C plays a role in the formation of two insoluble phases. And for understanding this, we have considered two solvents. We have considered the ternary equilibria obtained with these two solvents. With B1, you have the ternary equilibria is like this, and with B2, the ternary equilibria is like this. Okay, now let's understand further. So formation of two insoluble phases, that is raffinate and extract phases, For a given solvent, it also depends on the concentration of C in the A plus C solution, that is feed solution. And then I had shown this two equilibria, two ternary equilibria. ठीक है. So A plus C solution, in both the cases, only those A plus C solutions represented by points that lie between A and D. That means only those solutions lying between A and D. This the same understanding for this ternary diagram and this ternary. For this ternary diagram, all those A plus C solutions that are represented by points that lie between A and D. All those A plus C solutions that are represented by points that lie between A and D. So A plus C solutions represented by points between A and D, they can only form two insoluble phases with these solvents. So for example, for this ternary diagram, only solutions represented by points between A and D will be forming two insoluble phases with solvent B1. And in this case, only those A plus C solutions lying in this represented by points between A and D will be forming two insoluble phases with solvent B2. Are you understanding it? So if you cross D, if you let us say that you consider a point, and the A plus C solution at this point will not be separated into two insoluble phases using P1. Similarly, for this ternary diagram, a solution represented, A plus C solution represented by this point will not be separated, or it will not be separating into two insoluble phases using solvent B2. So if you compare these two ternary diagrams with each other, the diagram number 1 and diagram number 2. In diagram number 1, B is more insoluble in A plus C solution, whereas in diagram number 2, B is more soluble in A plus C solution. So we are interested in the region beneath the binodal solubility curve. Any point beneath the binodal solubility curve represents a ternary mixture where there are two insoluble phases, and any other point outside the binodal solubility curve, it will be representing a single liquid solution. I have discussed this in my video on binodal solubility curve. A link is available in the description section. You please watch that video. So only these solutions, they can be extracted with solvents B1 and B3. With solutions, all those solutions which are represented by points that lie between A and T. All those solutions represented by points that lie between A and T. Only these solutions can be extracted with solvents B1 and B2. So in this case, B1 is more insoluble because the insolubility region, the area occupied, the insolubility region is larger in the first case. And that's why B1 is more insoluble than B2. And that's why it is a better choice in this case. It is a better choice in this case. So I hope you have understood how insolubility of the solvent in the original solution or in the feed solution decides its selection. So what is our conclusion? A solvent that is insoluble to a greater extent in the feed solution needs to be selected, because that will help in easy formation of the two insoluble phases, raffinate and extract phases. ठीक है. Then you have the other point is solvent recoverability, because if you are using a solvent in the extraction, then at the end of extraction or after extraction is complete, you need to recover it so that you can use it in new extraction operation. Then and then only it will be economically feasible. Okay, so that's why liquid extraction will be economical when if the solvent is recovered and then reused in new extraction operation. So solvent used in one extraction operation, at the end of that operation we need to recover it, and then you can use that recovered solvent in new extraction operation. Only then liquid extraction will be economic. The solvent recovery is done by using some other mass transfer operation. So we need to use some other mass transfer operation in order to recover the solvent. And the most famous mass transfer operation is distillation. Frequently used mass transfer operation for recovering the solvent is distillation. And if distillation has to be used, then you need to consider few points. What are these points? Let us understand. So if distillation has to be used, the following points must be considered. First thing is, the solvent should not form an azeotrope with the extracted solute. So at the end of extraction, you are going to get an extract phase. Extract phase is nothing but solution of solvent and the solute. So you'll be extract phase will be B plus C, and you need to recover the solvent, and for that you need to separate B and C, B from C. And the most frequent operation is distillation. And if you are using distillation, then this solution should not form an azeotrope, because if this forms an azeotrope, you will not be able to separate it by using distillation. So the solvent should not form an azeotrope with the extracted solute. This is one thing. Then the extract phase, which is solution of solvent and the extracted solute, solvent plus extracted solute, should have a high relative volatility. High relative volatility will be helpful because it will reduce the recovery cost. So you need to select a solvent which will have, after forming the solution with the extracted solute, it will be having, or it should have, a high relative volatility. Then the component in the extract phase, it could be the extracted solute or the solvent. Extract phase will have two major components, the solvent and the extracted solute. The component in the extract phase, either the extracted solute or the solvent, whichever is present in lower amount, it should be more volatile. So if B is in lesser amounts, it should be more volatile component. If C is lesser component, is in lesser amounts, it should be more volatile. So the point is, the component that is present in a lower amount should be more volatile. Again, you have to choose a solvent which will result in this situation. Which situation? The component that is present in lesser amount, it will be more volatile. So if this is done, then the heating cost will be lower. That will reduce the heating costs, because you need to vaporize little amount of a component, the component that is present in lesser amount. If solvent is more volatile, if the solvent happens to be the more volatile component, then you choose a solvent whose latent heat of vaporization is lower. Again, that will reduce heating cost. So these are the points that you need to consider if distillation is to be used for separating the solvent. You can use other mass transfer operations, but frequently distillation is the operation that is used for recovering solvent. Okay, so if distillation is to be used for the recovery, then the selected solvent, you need to consider this point. In the selected solvent should not form an azeotrope with the extracted solute. should form an extract phase that has a higher relative volatility with the component in lesser amount as the more volatile component. It should have a low latent heat of vaporization. If it is the more volatile component, if the solvent is the more volatile component in the extract phase, then it should have low latent heat of vaporization. So, solvent recoverability, if you are using distillation for recovering the solvent, then you need to consider all these points while selecting the extracting solvent. Okay, so I hope the point is you need to recover the solvent. And in short, you can say that you'll be selecting that solvent which is easy to recover or whose recovery is not unduly costly. Okay, so that leaves our discussion on solvent recoverability. Let us move ahead. The next criterion is density difference. What is this? A difference in densities of the raffinate and extract phases is required. Why it is required? It is required for effective separation. We need to have a difference between the densities of raffinate and extract phases for effective separation. So if I denote rho difference as difference between density of the extract phase and raffinate phase, in this case rho E is density of the extract phase and rho R is the density of the raffinate phase. So larger the density difference, the better would be the separation. Larger the density difference, better the separation. So the rho diff should be larger. For ternary systems, like the one I have shown here, the binodal solubility curve. In this case, C is soluble in A and B, and A and B, they are soluble in each other only to a limited extent. So in this case, you have the plate point. I have discussed all this in my video on binodal solubility curve. It is there in the description section. Now, rho diff, that is density difference, it will decrease with increase in the concentration of C. So as you move from side AB to C, that is as the concentration of C in the mixture increases, density difference decreases. And density difference becomes zero at the plate point. At the plate point, there is no difference between the density of extract and raffinate phases. In some cases, what happens? Rho difference is positive, that is density of extract phase is greater than that of raffinate phase up to certain concentrations of C, and then it becomes negative. That is, after some certain concentrations of C, rho R becomes greater than rho E, in which case this rho difference, it will become negative. So there are cases, in some cases rho diff is positive up to certain concentrations of C, and then it becomes negative. So if for these cases, the density difference becomes zero before reaching the plate point. In most of the cases, it will become zero at the plate point, but in some cases where density difference is positive up to certain concentrations of C, and then it becomes negative, in that case, density difference becomes zero before reaching the plate point. Anyway, as zero density difference is not desirable. And this is especially true in the case of continuous contact equipment. So what is the idea, or what is our conclusion? We are going to select a solvent that gives higher values of density to us. So you select a solvent that will give a larger density difference between raffinate and extract phases. Okay, next criterion is interfacial tension. So this represent adhesive forces at the interface between two immiscible liquid phases. And in liquid extraction, solvent and feed solutions, they are immiscible in each other. Higher interfacial tension, it favors coalescence rather than dispersion. Coalescence, that is where the two immiscible phases, they try to mix together. So higher interfacial tension, it favors this coalescence rather than dispersion of one phase into the other. So coalescence, it promotes the formation of extract and raffinate phases, and coalescence is favored by higher interfacial tension. So our conclusion is a solvent that produces higher interfacial tension would be a better choice, because higher interfacial tension will favor coalescence, which will promote the formation of extract and raffinate phases. So we are going to select a solvent that produces higher interfacial tension. That would be a better choice. So based on interfacial tension, you need to select a solvent that will produce higher interfacial tension. So besides all the criteria that I have discussed till now, there are some miscellaneous criteria that also have to be considered while selecting the extracting solvent. So for example, let me list those criteria. The solvent to be selected, it should be chemically stable. It should not it should be chemically stable. It should not react. It should not decompose. It should be chemically stable. It should be chemically inert towards other components that are present in the system, and even towards the material of construction of the equipment. It should have low viscosity. It should have low vapor pressure. It should have low freezing point, because all this are necessary while handling and storage of solvent. For easier handling and storage of the solvent need to have low viscosity, low vapor pressure, and low freezing point. The solvent should be non-toxic. It should be non-flammable. It should not be unnecessarily costly. So this miscellaneous criteria also have to be considered while making a choice for the extracting solvent. So finally, let us summarize all these points. The solvent selected for extraction should give selectivity greater than 1, that is beta greater than 1, should give higher values for the distribution coefficient, that is K. It should be insoluble to a greater extent in the feed solution of A and C. It should be easily recoverable for reuse by using other mass transfer operation, and most frequent one is distillation. And if it is distillation, I have told you how to, or what points you need to consider if you are using distillation as the mass transfer operation for separating or for recovering the solvent. It should provide greater difference in the densities of raffinate and extract phases. It should produce higher interfacial tension when mixed with the feed solution. It should be chemically stable. It should be chemically inert towards other components and also towards the material of construction. It should have low viscosity. It should have low vapor pressure. It should have low freezing point. It should be non-toxic. It should be non-flammable, and it should not be unnecessarily costly. So this summarizes all the criteria that have to be considered while making a selection of the extracting solvent. We need to consider all this because no single liquid will be an ideal solvent. That is, a solvent that will have all the desirable properties. So you need to make a compromise. That is important. So with this, I end my discussion for this particular topic. Very important topic. You should know how to select extracting solvent for the given task of liquid extraction. You should be able to describe each and every criterion for selecting the extracting solvent. So I hope you have learned something through this video lecture. And with this, I end my discussion for today. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. And do hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. Because I'll be adding more videos to my channel on the topic of liquid extraction. For now, have a nice day. Bye bye, and do join me in my next video lecture. Thank you.